Today we're going to talk about a data structure called a heap. We can use a heap to create a priority queue. What's a priority queue, do you ask? Well, first let's talk about a regular queue. If you go to the grocery store and you get in line to check out, well, the first person that got in line is the first person that's checked out, or FIFO, first in, first out behavior. That's a normal queue behavior, and that works well in the supermarket. But let's say that we're in the emergency room at the hospital and there's someone that's critically injured, but they're the last person in line. We want to have the ability to have that person jump to the front of the line and get immediate attention. A heap is a fast and efficient way to implement a priority queue. The rules for a max heap is that the parent nodes have to be greater than the children. For a min heap, that'll be different, but we're using a max heap here. We also need a complete binary tree, meaning you've got two children for each of the nodes except for the last row where you may have 0 or 1 children. You'll always fill in the left child first and then the right child. An array is a popular choice when implementing a heap. We'll put our root in position 0 and its children in positions 1 and 2, and then fill in the array this way. Now let's get to the code. So I'll make a Python class to hold on to everything about a patient, their name and their priority. We'll just hard code the 5 patient values. So we'll start with Bobby, Sue, John, Alice, Mary, and we'll put them in the right order to start out with. Let's go back to our tree and add a new item. Let's add Ben, who just came into the emergency room. But now our heap property doesn't work. We need the parents to be bigger than the children. So we're going to upheap and promote Ben until he becomes our new root. In array form, use this mathematical formula to figure out the node that's Ben's parent, the index that you need to check to see, is it smaller or bigger than Ben? If it's smaller, you'll switch spots. Recursively do this until you're back to the top of the array or you don't have any more swaps. Let's jump to the code and add Ben. And Ben's going to be added to the heap. But when we print the heap, we see, yeah, this is not right. We don't want Ben to be in the last position because he's the highest priority. So figure out, using our mathematical formula, what is Ben's parent's position in our heap, our array, and then compare, is the priority of Ben bigger than his parent? If it is, do a swap. Add this to a while loop, so it's recursively going to do this until there are no swaps left to do or we're at the top of our heap. We just need to print the heap and verify everything's in the right order. What happens if we remove a patient from our heap? Well, we always remove the root node, so we remove Ben from the heap. And then we need to replace that root with something, so we will take the last thing that was added to the heap and put that in the root position. Well, our heap property may not be satisfied, so we need to downheap. Compare it with both of its children. Whichever child is biggest needs to become our new root. You may need to do this recursively if you have a bigger tree. Let's look at it in array format. Position 0 has our maximum priority. Pull that out and replace it with the last item in the array. Use these math formulas to figure out the 2 children of this new root, and then you'll figure out if one of them needs to become the new root. Now we can demo removing from the heap in our code. Instead of removing it, I'm just going to replace the root value with our child value, effectively removing it. And then let's create a while loop that's going to say, well, we still have some downheaping to do. We're going to keep making those switches. And we want to stop the loop if we ever reach a point where we haven't made a switch. Here's some formulas for finding the left and the right child, so we'll know what to compare our root with. And I'm going to add a for loop here so we can print out and see that we're getting the correct values. Well, that was a lot faster than most of my videos. I want to slow down for a second and show how I could make something a little bit more general purpose where I don't hard code the different values of my patients in my priority queue. I'll keep the heap node class, and instead of hard coding exactly who's in the heap, I'm going to make an add to heap and a remove from heap function. And then I'm going to have to let the user decide
who they want to add and when they want to add someone, when they want to remove something from this priority queue. So if when they run it, the user can say, yeah, I want to go ahead and add someone to the queue. Let's add Bob, and his priority is 12. And then we'll print out the heap. So I kept my same logic to print whatever is in our priority queue, which is our heap. And then I could add someone else. And if I add somebody with a higher priority, we're going to see them jump to the top of that priority queue. If we want to remove somebody, we'll try typing in 2. It should always remove the root, the person with the highest priority problem. And then, we'll have Bob left over we could remove from the root. So in case you wanted something a little bit more general where you can decide how many values are in the heap, I've got this code here, and I'm using the same logic to figure out when you're adding somebody to the heap, you always add that person to the end of that array, or in Python, it's called a list, and then you do your up heap logic. And when you want to remove, well, you're always going to remove the person that's got the highest priority, and they're always sitting at the top. So I'm printing out the name and the priority of the person in the very first position of my list. And then instead of shifting everybody over, we are going to be doing that down heaping. We will replace that position that we are removing, that person that was on the top of that priority queue, the top of the tree, we're going to replace them with the person that was in the last position. And we're doing that right there. And then, so our heap is now 1, the length is 1 less than it was before. We do our down heaping just to make sure we have that heap property. Again, I'm using a max heap. If you're doing a min heap, you're going to be changing all my greater than signs to less than if you want the smallest values to bubble up to the top of this heap. All right. Hope you enjoyed this lecture. If you have any requests for future data structure lectures, put them in the comments section. Happy programming.